Section 10.2, machines. You guys should have learned a lot about machines when you had 9th grade physical science, and we're going to add to what you already learned to your background knowledge on machines. So before we start the machines, what is a machine? Well, machine is pretty much anything that eases the amount of work that we need to do. And how does it ease the amount of work? Well, it's going to change the magnitude, how much force, or the direction of the force in which we have to do it. So it's going to help ease the amount of force or the direction of the force for which we have to do it. Machines are a part of your everyday life. They're super easy. They help you out. You don't even think of even the most basic simple machines. So when we talk about simple machines, what are the 6 simple machines? Lever, and we'll talk a little bit more about what a lever is, or the 3 different branches of levers in a second. Pulley, inclined plane, wheel and axle, wedge, and last but not least, screw. Now one could argue that a wedge and an inclined plane are almost the same thing. If you have a 90-degree triangle like a block of wood, it is going to look like a wedge. But it is going to act as an inclined plane. So an inclined plane and a wedge are different. So those are 6 types of classic simple machines. When we talk about machines, we have to talk about 2 things. We have to talk about mechanical advantage and ideal mechanical advantage. And what is mechanical advantage? Mechanical advantage is really how much advantage is that machine giving us. So when we calculate mechanical advantage, the equation is mechanical advantage is equal to Fr divided by Fe. What is Fr? Fr is the force of resistance. The force of the resistance is the force done by the machine, divided by the force of effort. What is the force of effort? What do you think effort is? Effort is the force done by you. So when we take force of resistance divided by force of effort, we are taking the force of the machine and dividing it by the force of effort, which is what you've done. All right. Ideal machine. In an ideal machine, the effort you give is the resistance you give. However, machines are not always 100% efficient. So when we talk about an ideal machine, the amount of work you put in is the amount of work you get out. So WO is work out equals work in. Now that would be an ideal machine. All the work you put in is the work you get out, but that's not necessarily the case. What holds machines back? Friction is a big key. And there are other outside forces which also prevent machines from being a 100% ideal. But we are going to spend a little time calculating an ideal machine. And an ideal machine, work output is equal to work input, or remember that work is equal to force times distance. Work output is the work done by the machine, so that's Fr times dr. That's equal to work input. The work input is the work done by you, so that would be force of effort times distance of effort. Now we just talked about mechanical advantage. We're talking about ideal machines. There is my ideal mechanical advantage. What would be the best thing that you could get out of that machine? So ideal mechanical advantage for the machine. For an ideal machine, IMA, we abbreviate ideal mechanical advantage. IMA is equal to DE divided by DR. Now DE is the distance of effort. Now remember that distance of effort is done by the person or you, and the distance of resistance is dr, the distance of resistance, and that is the distance done by the machine. In an ideal machine, our mechanical advantage is equal to ideal mechanical advantage because we are not losing any of our advantage. However, that is not the case. In real machines, mechanical advantage is much less than ideal mechanical friction due to the things we talked about earlier. Friction, and all their outside forces. So we have mechanical advantage, ideal mechanical advantage. And that can also calculate work output or work input. Now work output, remember, is what the machine is doing. So that deals with our force of resistance and our distance of resistance. Work input is equal to the force of effort times the distance of effort. Now we can have another equation, efficiency. Efficiency is equal to work output divided by work input, or it is equal to mechanical advantage divided by ideal mechanical advantage. So efficiency, work output divided by work input, or efficiency, mechanical advantage divided by ideal mechanical advantage. And when we sit there and do an example using all these equations, the biggest thing that you're going to be challenged with is trying to figure out where the forces and distances and if they're effort or resistance. So the big idea here is sit down and figure out before you start any of your questions what exactly you're dealing with. You have force of effort, force of resistance, distance of effort, distance of resistance, work output, work input, or efficiency, or ideal mechanical advantage or mechanical advantage. So there's a lot of variables that you have to think about. So before we even look at the questions, let's read the problem and figure out what we have. A bottle opener requires a force of 35 newtons applied to the handle in order to lift the bottle cap 0.9 centimeters. The opener has an IMA of 8.0 and an efficiency of 75%. Well, let's write down here below what we have. First things first, a bottle opener requires a force of 35 newtons applied to the handle. Are you applying the force or is the machine applying the force? It's applied to the handle, so you are applying the force. So the force of effort is 35 newtons. Next up, apply to the handle in order to lift the bottle cap 0.9 centimeters. Think about how this would work. Are you lifting the lever or are you lifting the bottle cap? You are lifting the lever. Therefore, the lever is lifting the bottle cap. So the machine is lifting the bottle cap 0.9 centimeters, which means that the distance of resistance is 0.90 centimeters. The opener has an IMA of 8.0 and an efficiency of 75%. So those are the four pieces of information given to us in the question. Question A, what is the mechanical advantage of the opener? Well, we have mechanical advantage is equal to, we have the force of effort the force of resistance divided by the force of effort, but we don't really know that. We don't have force of resistance, so we can't calculate that. But mechanical advantage, efficiency is equal to mechanical advantage divided by ideal mechanical advantage. Well, we have ideal mechanical advantage and we have efficiency, so we can go ahead and plug that in. 0.75, because that would be 75%, is equal to MA over 8.0. 8.0 times 7.5, and we get that our mechanical advantage is equal to 6.0. Because it is a ratio, we're taking newtons divided by newtons for mechanical advantage. There is no unit. So mechanical advantage is 6. There is no mechanical advantage there are no units for mechanical advantage. So in part A, our mechanical advantage is 6. B, what is the force applied to the bottle cap? Well, we talked about you are applying a effort to the lever, and the lever is moving the bottle cap. So any force of effort or distance of effort would be the lever. Any force of resistance or distance of resistance would be the bottle cap. So we are trying to find the force of resistance. Well, we can do that based upon MA is equal to FR divided by FE. We're trying to solve force of resistance. We know that MA is 6.0. Force of resistance is what we're trying to solve for, and our force of effort on the bottle cap was 35 newtons. 6 times 35, and we end up that the force applied to the bottle cap, or our force of resistance, is 210 newtons. Lastly, part C is asking how far does the handle of the opener move? Well, remember, we've been talking about you are moving the handle is moving the bottle cap. So your effort is moving the handle. So we are trying to figure out the distance of effort. Well, can we do that? Most certainly. How? Well, ideal mechanical advantage is equal to dE over dr. We know the ideal mechanical advantage is 8.0. We're trying to solve for dE. And our dr is 0.90 centimeters. When we solve for this, we get our distance of effort is 7.2 centimeters. So the real big catch when you're doing this is understanding what the effort is and what the resistance is. And remember, the effort is what you are doing. The resistance is what the machine is doing. So you are always doing something to start, and then that is the machine to accomplish your goal. We will continue to work with that because the biggest thing in this chapter is trying to figure out whether or not it's an effort or resistance. So we will continue to work with that. To finish this up, we talked about, earlier, we talked about levers. So when we talk about classes of levers, there are 3 classes of levers, and each lever is classified where the effort is, where the resistance is, and finally where the fulcrum is. And on a lever, the fulcrum is simply the pivot point. So there are 3 classes of levers because we have fulcrum, effort, resistance, and they can be rearranged. So when we talk about classes of levers, we have our first type of lever, first class lever. The fulcrum falls between the effort and the resistance. So we have a lever, we have the fulcrum, we have the effort, and we have the resistance. What common objects are first class levers? The fulcrum is in the middle, our pivot point's in the middle. Well, right away it looks like a seesaw, but what other common machine would be a first class lever? Any guesses? That's scissors. Think about it. Your effort is the handle. You're holding the handle. You're pressing the handle down. The fulcrum point is the pivot point where the scissors moves, and the resistance is the paper you are cutting. So the effort, fulcrum, resistance. The fulcrum is in the middle when we talk about a first class lever. Second class levers. All we're doing is we're rearranging where our effort, resistance, and fulcrum falls. So in a first class lever, the fulcrum was in the middle. In a second class lever, the resistance is in the middle. So our resistance is in the middle. And our effort is on the end. Does anyone have any idea? Actually, yes. Does anyone have any idea where a fulcrum's on the end? Our pivot point's on the end. Our resistance is in the middle. Anyone ever use a wheelbarrow? The wheel's on the wheelbarrow or the fulcrum. Where's the weight? The weight is the resistance. The resistance is in the barrel. And then where's your effort? You're lifting the handles. So a second class lever would be a wheelbarrow. Also, if you think about it, it's holiday season. My family enjoys walnuts and all types of those nuts. My mom buys a big bag, and you have to crack open all the fresh nuts. Think of a nutcracker. Where's the fulcrum on a nutcracker? On one end. Where do you put the nut? in the middle, and then you are grabbing the handle and pressing down and breaking the nut. So examples would be wheelbarrows or a nutcracker for a second class lever. So our first class lever, we had the fulcrum in the middle. Our second class lever, we have the resistance in the middle. And for our third class lever, our effort is in the middle. Our fulcrum still on one end. We have our effort in the middle and our resistance on the outside. The third class lever, you guys might use the third class lever every single day. In fact, a third class lever is going to buy Danny Wagner a nice scholarship. So go figure out what a third class lever would be real quickly. A bat. Any object you swing is going to be a third class lever. Where's your pivot point on a bat? Essentially the bottom of the bat. The bottom of the bat is where it moves. Where's your effort? Right on the handle where your hands are. That is the effort. And where's the resistance? When you hit that ball, you're hopefully not hitting it on your hands. You're hitting it out on the bat. So that is resistance. Also think of a broom. Where's your pivot point on a broom? Right at the top. Where's your effort? In the middle where your hand is sweeping is where's the resistance? The resistance is the floor. So examples of third class levers would be a baseball bat, a broom, a tennis racket, anything you swing. A hockey stick would even be a third class lever. Where's the pivot point? The top of the handle. Where's your effort? In the middle. And where's your resistance? The puck. And where are you hitting the puck? You're hitting the puck on the bottom of the stick. So three different classes of levers, all combining what we talked about in the previous slides, figuring out where our resistance and effort are. On a first class lever, the fulcrum is in the middle. On our second class lever, the resistance is in the middle. And in our third class lever, the effort is in the middle. And we will go through identifying types of these, and you will have problems on simple machines tomorrow in class.